All right, so we're gonna go ahead and finish up this problem from class. So just as a review, we're taking a look at part B here, where now we have friction as this thing slides up. So we drew an energy bar chart for here. So we said at the beginning, it starts with all kinetic energy. As it gets to the top, it's actually gonna lose some energy, and it's gonna have actually less gravitational than it started. So energy is being transferred out of the system, or negative work is being done. So we have some kinetic energy, that's our initial energy, minus the work being, or the energy being removed from the system, is equal to the final gravitational energy. So we want to find the new maximum height, and again, it has no kinetic energy, because when it reaches its maximum height, it has to not be moving, and no elastic energy since we have no spring to store energy here. So we took this equation and rewrote it. So the kinetic energy being 1/2 mv initial squared, negative work, and then the final energy being mgh2, where h2 is the new height that we're trying to find. Well, because we knew that work is FD cosine of an angle, and in this case, since theta was already the angle of incline, we're going to use phi, not to get those confused. So phi is the angle between the force vector and the displacement vector, and theta is the angle of the incline. So we know that the force causing this transfer of energy is the force of friction. The distance which it acts is h2 over the sine of theta, which was given to us right here. And the cosine of phi turned out to be -1, because the displacement vector, or the distance which it's going, is up the incline, and the force of friction is down the incline. So we have an angle of 180 degrees between those two vectors. So that becomes -1. So this becomes positive, and we have 1/2 mv squared plus the force of friction times the distance h2 over sine of theta equals mgh2. Now the problem was that we're asked to determine the new maximum height in terms of the given quantities, which are going to be m, v0, mu, and h2 sine of theta. Ff, or the force of friction, is not a given quantity. So that means I want to get rid of it. Well, I want to get mu in here somehow, so we remember that the force of friction is mu times Fn. So I can make that substitution, and I get mu Fn here. Well, again, the problem is still that the normal force isn't a given quantity, so I'm going to get rid of the normal force. And the way I can do that is by drawing a free body diagram. So we know we have force of gravity acting straight down. If this thing's sliding up the incline, the force of friction must oppose that motion down the incline. And the normal force has to be perpendicular to the surface. So there is our normal force. Now the force of gravity, since it's a 2D force here, we're going to break it down into its components. So we have Fgy here, and then Fgx. And we have our angle theta. And that angle is always between the gravity vector and the y-axis. So here, if I sum the forces in the y direction, they have to be some net force. We know our net force can either be 0 or ma. In this case, in the y direction, so in this axis here, the box is not accelerating in the y direction, so I know it has to be balanced, or that my net force has to be 0. So out of the two options, it must be 0. Fn positive and Fgy negative. So I know Fn equals Fgy. Fgy is the adjacent side of this triangle, so it's going to be the hypotenuse, Fg, times the cosine of the angle, or that Fn equals mg cosine of theta. So a quick review of the last section of forces there. So I can make that substitution. 1/2 mv0 squared plus mu mg cosine of theta h2 over the sine of theta equals mg h2. All right, so now this equation is getting a little annoying in terms of algebra, but some quick things that I do notice. M in every term, so I can cancel that out. And likewise, I have a cosine over a sine. So that's going to become a cotangent. So I have a 1/2 v squared, or v0 squared over 2, plus mu g cotangent of theta h2 equals gh squared. Okay, so now this looks like it's getting a little more reasonable to deal with. To make sure I have enough room, I'm going to go over one slide. So let's see, v0 squared over 2 plus mu g cotangent of theta h2 equals g h2. Is that correct? All right. So I'm going to get the mu g cotangent theta onto the other side. Okay, so let's see. Now I can factor out a g and an h. So let's see, 1 minus mu cotangent of theta. And this tells me then that h2 is divide g into 1 minus mu cotangent theta out. So that's v0 squared over 2g times 1 minus mu cotangent of the angle. And there's a new height it'll reach. So this problem really tests your understanding across multiple disciplines. So it uses both energy, work, and forces. And that's actually pretty common what you'll see in AP Physics questions. As often, you'll have to start out with a conservation of energy equation. Remember to include work. You'll have to use the definition of work, realize that you'll have a force that you need to take care of, and then end up using forces to write the answer in the way that AP wants. So in other words, only having it in terms of given quantities, so in this case that's v0 squared, mu, theta, and then or universal constants such as g.